Good morning. My name is Emanuele Di Lorenzo from the Georgia Institute of Technology, and I'm very honored to give the Ocean Extremes New Horizon talk, and so thank you for inviting me to talk today. The first thing I did this morning was to ask Alexa to show me an image about extremes, ocean extremes, and this is what Alexa showed me. As you can see, most of these pictures are whales and nice pictures of the ocean, lighthouse. So obviously a very different type of pictures, because if you ask Alexa about climate extremes, the pictures that emerge here are a lot more technical and more close to the type of science pictures that we're expecting. So it is obvious that the emergence of ocean extreme terminology is relatively new, and is really motivated by the recent appearance of these unprecedented marine heat waves. And in fact, when you search Alexa and Google for marine heat waves, you get, the type of imagery, technical science imagery that we are more accustomed to. And in fact, you can find also a definition for a marine heat wave as a short period of abnormally high temperatures in sea or ocean. And there's really nice papers for maybe starting back from Hobday et al. 2018 that have characterized and classified these heat waves in the observational record with intensity, duration, frequency, and other shape. So in fact, actually, I want to give a kudo to a group that has put together this nice website called marineheatwaves.org. These are some of my favorite authors, including Neil Holbrook, Eric Oliver, Alistair Hobday, who are good friends. And if you look at this type of literature, you realize that the focus on marine heat waves really began with some recent high-profile events, which are summarized in this picture by a paper of Thomas Fröhlicher on the emerging risk from marine heat waves. And what is evident in this picture is that these events target specific regions, and even though in the definition they're called short events, some of these events are not short. They've actually lasted for quite a while, as you can see in the southern tip of Australia, as well as in the North Pacific. In fact, following these papers, there was some work that tried to essentially attribute the emergence of these episodes to climate change, both in the observational record by Eric Oliver, as well as in using climate model projections by Thomas Fröhlicher and Gruber and al. And these, I'm not going to dwell on these papers. You can look at them. What's interesting, though, is a recent paper from Lotforther in Science in 2020 also revealed that these particular targeted areas are also where, if we look at different statistics like duration and peak temperature anomalies, these really pop out as being recurrent throughout the observational record. So it's not just those specific events, but it's kind of a statistically reoccurring kind of phenomena. Furthermore, Holbrook, Neil, wrote a nice paper that I actually had the pleasure to review on a global assessment of marine heat waves and their drivers, and recognized that a lot of these heat waves are really connected and linked to these climate modes. And so that really is a clue that the dynamics of these events are not separated by the dynamics of climate variability as well. And with that said, today I'd like to focus on really some of the Pacific climate mechanisms that drive these marine heat waves, both the duration and intensity, and then discuss some of the recent changes that we've seen in Pacific climate and these mechanisms and how they've impacted the statistics of marine heat waves. I also then want to discuss the role of anthropogenic forcing, and in specifically how anthropogenic forcing has changed the mechanisms that drive heat waves. So a lot of studies have looked at the attribution from a statistical standpoint. I'd like to look at some of the mechanisms that could be involved to really change, the way that the climate in the Pacific is working. And then last, I won't have time, but I wanted to just make a few remarks about the marine ecosystem response to these more frequent ocean extremes. Now, with that said, the first part is really about the Pacific climate mechanisms that drive heat waves, and in particular, I'm going to focus on intensity and duration. And here a caveat that is that I will discuss mostly work from my lab to feature these young talents, Tong Tong Su, Ying Zhao, Giovanni Liguori, who is now a postdoctoral scientist in Australia, and Youngji Zhou, who is a postdoctoral fellow at GFDL in the United States. So with that said, I'll start by looking at a particular case study, which is perhaps on the mind of many, which is a warm blob that happened in the North Pacific between 2014 and 2015. And these are the temperature anomalies that occurred in the winter of 2014 and persisted throughout the winter of 2015. And you can see that this is a big mass of warm water in excess of, in some places, 3 degrees C. That really is the size of the United States. So it's pretty massive. And what I'm going to show you, is that this oceanic heat wave is really connected to atmospheric forcing, in particular to the persistency of atmospheric weather patterns that are also referred to as atmospheric waves. And so to do that, first a short primer on these atmospheric waves. This is a picture showing the jet stream and its characteristic kind of ridges and troughs. These are essentially the high latitude Rossby waves. And associated with that, we have regions of low and high pressure that essentially move with the wave. But every so often, these waves are arrested, or there's some in the blocking in the atmospheric literature. And these non-propagating waves tend to amplify in place so that the lows and high tend to grow. And so over land, of course, you experience persistent rain or persistent droughts, like happened in North California. But over the ocean, what you experience, essentially, you experience persistent forcing condition that is predominantly of one sign. And I will show you with a simple model what are the impacts of these resilient atmospheric ridge, in particular for the event of 2014. So to do so, I'm going to start by measuring the warm anomaly that happened during the warm blob in 2014 with a simple sea surface temperature average index, which is shown here. You can see the big event here in 2014 that is unprecedented over the historical record. And I'm going to now look at what was the atmospheric pattern during the 2014 event. And here you can see in sea level pressure anomalies, and this is sort of the wavy pattern which is associated with what was referred to as the resilient ridge. What we can do now is we can make a temporal index of this resilient ridge by just taking this pattern and projecting it onto the sea level pressure anomaly field. And this is essentially the record of pressure, which is in this period of time when the blob occurred. There's nothing visually appealing or strong that comes to mind. However, if we now essentially integrate this atmospheric pressure, essentially we mimic the oceanic response to atmospheric forcing. That is, that the rate of change of the oceanic temperature is driven by this atmospheric forcing, in this case the sea level pressure. And then of course we have a decay term of the sea surface temperature, meaning that once the temperature is perturbed, it will come back to some sort of zero anomaly within a time scale that in the North Pacific is about 8 to 12 months. This model is also referred to as an autoregressive model of order 1 and has been used in many studies as a simple model for ocean climate. And so what we're going to do now is we're going to take this sea level pressure index and essentially put it through this sea level pressure AR1 model. And this is in black the reconstruction of the model, which is able to capture this extreme event. And so really what this is saying is that this period of time was characterized by essentially sea level pressure drivers that were consistently more of one sign. And even though there wasn't a very strong particular event, the cumulative effect of these kind of same sign event essentially raised this anomaly in the ocean and made it grow. So this is essentially the idea that this persistent weather is really important in driving the intensity. And I believe even from Neil's nice paper that this is a general result that applies everywhere in the ocean and everywhere for these heat waves. The sea level pressure here is taken as an index of atmospheric forcing, but it's really a cumulative index in a way because it also includes effects of heat fluxes and so forth. So very good. So now the question though remain, what climate mechanisms link these two patterns? Obviously, it is there was a question about whether the 2014 and 15 kind of patterns were connected or disconnected. And what I'll show you is that they were actually connected through large-scale teleconnections in the Pacific, and in particular coupling between tropics and extratropics. And a clue to that is if we look at those pattern of those particular blob events in 2014 and 15, they really look a lot like the patterns of recurrent climate modes of variability, in particular in 2014, the North Pacific gyre oscillation. And for 2015 event, the pattern looked a lot like the Pacific Decadal Oscillation. And these are important clue because, in fact, the NPGO and PDO, even though the indices of these climate modes are independent, if we look at the 1-year lag correlation between these two indices, we find that these are not completely independent. In fact, there's a correlation of about 0.3 when the NPGO leads the PDO. Now, 0.3 is not a very high significant correlation, but if you actually look at this correlation in the observational record as a function of time, using a 20-year sliding window, what you find is that in the last 20 years, especially after 80, this correlation has gone way up. It's about 0.6, and it has, even though there's low degrees of freedom, is very significant here above the 0.43 correlation threshold. And so this suggests that there's been intensification of this coupling between these two modes. This result was also sort of explored in ensembles of climate models to see how robust it was. And this is an example from the Community Earth System Model Large Ensemble, which essentially shows the same trend of increasing coupling between the NPGO and PDO all the way to 2100, suggesting that this is some sort of signature of anthropogenic forcing. Now, going forward, the question now is, what are the climate mechanisms that link these two patterns? And I think to understand that, we have to go back to the NPGO pattern, and in specifically the pattern of atmospheric sea level pressure or atmospheric variability that drives the NPGO, which is shown here. So we have a dipolar structure in the sea level pressure, which close to the tropics is really the winds tends to produce a weakening of the trade off equatorial winds. And this is important because a weakening of the off equatorial trade winds will generate a reduction in the evaporation. And if you reduce the evaporation, the sea surface temperature will tend to warm. And the warming of SST has a positive feedback because it further reduces the winds. And so you get this kind of very important positive feedback, which in the literature is described as the wind evaporation sea surface temperature feedback. And through this feedback, essentially these warm anomalies tend to propagate in a rotating planet, and they propagate in a sort of southward, eastward direction and reach the tropics. Now, these dynamics of propagation of coupled ocean atmospheric kind of anomaly propagation towards the tropics are referred to as meridional modes, in that they propagate along the meridional axis. And there's a lot of literature here that is reported down below. And so through these meridional modes, essentially these sea surface temperature anomaly reach the tropics. And once you produce a warm anomaly in the tropics, this has the ability to impact the El Nino Southern Oscillation System, and in particular, the shifts in convection, which is shown here with highs and lows anomalies. And these shifts in convection generate an atmospheric response with the atmospheric Rossby waves that are the teleconnection patterns, which carry back the signature into the extratropics. And here is shown the sea level pressure anomalies, which is really the surface expressions of these atmospheric waves. And once you have an anomaly in the atmosphere, again, the atmosphere will drive an oceanic response in the sea surface temperature. And so through this mechanism, you get essentially, in summary, a chit-chat between the North Pacific sea surface temperature in one winter and the North Pacific temperature in the following winter. And specifically for the warm blob, the phenomenology here summarized is that during the winter of 2014, we had a strong atmospheric ridge, which generated the warm blob. The atmospheric, response, or the atmospheric driver of the blob, also triggered these meridional modes through the west feedback, which energized the ENSO system, and then the ENSO teleconnections essentially reinforced and persisted the warm blob in the next winter. Now, this nice mechanisms that was shown in a paper by Di Lorenzo and Mantua is not unique of this particular, warm blob event that happened in 2014-15. And in fact, a more recent paper by Tong Su showed that if you actually ask the question of what is the character of, prolonged heat waves in the North Pacific without any a priori assumption, and you run, for example, a simulation with an ensemble of many realization of Pacific climate, you find that in fact this particular phenomenology is very recurrent, and the duration of the heat waves is proportional to how engaged you get the tropics. So as you engage more the tropics, the duration of these heat wave increases. So I don't have time to go into details of the study, but I think this sort of corroborates this idea that the extratropical tropical coupling is really an important element for the duration of the heat waves. Again, going forward, I also want to mention that this sort of tropical extratropical coupling is really important not only on the time scale of the marine heat waves, but actually is a fundamental mechanisms by which you generate low frequency variability of Pacific climate. And there's a really nice study by Ying Zhao, which is sort of summarized in this, well, part of it is summarized in this picture, with the idea that, whenever you have internal stochastic variability in the northern hemisphere here, you can activate these ENSO precursors that then activate ENSO, and then you have ENSO teleconnections. And this whole loop, of time takes about a year or more. In this case, actually almost a year and a half. And that provides this kind of memory in the ocean that sort of allows to essentially take the high frequency variability in the atmosphere and redden it into low frequency variability of the ocean. Now, what's important here that this mechanism that I just described for the North Pacific also works for the South Pacific. And in fact, in this paper, Ying describes also the South Pacific component. And, unfortunately, not all models, and this is another study that she produced, can reproduce this mechanism very well because, as we know, climate models have issues with teleconnections from tropics and extratropics. But in a study of Giovanni Liguori, he actually looked at these kind of precursors from both the North and South Pacific. And in this study, he identified that there are very important differentials in the way that these precursors impact the tropics and then the tropical teleconnections. Specifically, he found that the North Pacific precursor really has a tendency of affecting more the ENSO frequencies in the tropics, whether the South Pacific precursor tend to impact more the low frequency. So this is kind of an interesting aside. But moving forward, what I wanted to bring up about Giovanni's work was this idea that the meridional mode, have increased their variance over the observational record, which is shown here in this picture. And so here we're getting into the mechanisms of why potentially the climate variance in these marine heat waves are increasing with climate change, in addition to the shift, for example, in the mean temperature. And so what is shown here is in blue here is essentially an index of the meridional modes in a climate model ensemble. This is a 30-member ensemble from the CSM. And so blue is the ensemble mean. The bluish light here is the spread. And so you can see that in the models, there's a very significant increase in the variance of the meridional modes. So this is essentially variability after we have taken away the trend, which in the ensemble mean is easy to do because you just average all the ensemble members. And this trend is also present in the observations, which are shown here in black. Of course, in the observations, we cannot assess the significance, but in the models, this is very significant. These other two plots in green show the same dynamic of the meridional modes from the atmospheric perspective. So these are the off-equatorial trade winds showing again a trend in their variance. And this trend is also present in the observations in black here. And together with that, there's also an increase in the ENSO variance, which is still largely debated, but it's shown in this particular model and also in the observational record to the extent that you trust the observational record. Now, the question now is why this increase in the meridional modes? So this is just some observational and modeling evidence, and the why really comes from looking at the dynamics of these modes, and in particular at a parameter that is important to understand the growth rate of these meridional modes. And this parameter is called the West parameters, and it's really the sensitivity of the sea surface temperature to a wind perturbation. So the way to read this plot is then when the West parameter is very high, that means that a small perturbation in the SST will produce a large response in the winds. And so if you have a higher West parameter, essentially when these modes start to grow, at the end of their growth, they will have a stronger amplitude. And a stronger amplitude means that once they're in the tropics, they have a more likelihood to impact ENSO. Now, if you look at this West parameter depends on the background mean state, because in a warmer climate, essentially the same SST perturbation will produce a stronger response in the evaporation, which is this West feedback. And that's because of the nonlinearity, in the relationship between, changes in SST and evaporation at different mean states. So the idea, this first mechanism is really that this kind of intensification of the West parameters, which is dependent on the background mean warming, essentially is energizing, making these meridional modes more energetic. So this is one possible mechanism for why the climate variance of the Pacific is increasing. Another mechanism is entirely different and really is related to coupling between tropics and North Pacific associated with the Kuroshio-Asho extension region. In particular, when you have an ENSO and you have the ENSO teleconnections, after a certain amount of time, you will also impact the Kuroshio-Asho extension region. Essentially, the atmosphere, produces, excites oceanic waves that reach the western boundary. And this is also, I think, work that Neil documented for the South Pacific western boundary. So what happens is when you activate the Kuroshio is very warm, and changes in the Kuroshio connection impact the atmosphere, and in particular the storm tracks, for example. And so they can actually generate a response, in the atmospheric forcing. And this response in the atmospheric forcing has been shown in this paper can actually activate these ENSO precursors as well. And so there is, in fact, a dynamic coupling between in particular, the Central Pacific type of El Niños and the Kuroshio through this kind of mechanism where the Kuroshio impacts the storm tracks. The storm tracks excite kind of a meridional mode or ENSO precursors. They impact the Central Tropical Pacific, and then there's teleconnections back that reach the Kuroshio. Typically, this whole loop takes about a 5-year to do one half loop, so that essentially this produces a decadal time scale. There's almost like an oscillation. And in fact, in a follow-up paper, Young-Ji Zhou showed that there's an important, coupling at the decadal timescale between the Kuroshio and Central Pacific El Niño, which is shown here. This is a cross-correlation function between an index of the KOE low-frequency variability and the Central Pacific El Niño. And you can see that there's this very important sinusoidal shape with the period here of 10 years. And what's important in this paper is that this particular sinusoidal coupling actually increases over the last 30 years, and this increase is not random. In fact, it's very statistically significant, and I'm not going to be able to go through all the ensemble modeling that took place. But the bottom line is that there's a significant intensification of this coupling between KOE and CP. And one of the hypotheses from this paper is that the warming of the KOE generates an atmospheric response in the position of the storm track that is more likely to, in fact, activate this cycle. So essentially, this kind of shift in the storm track, associated with this KOE, is more likely to energize this cycle. So this is, again, is another mechanism for increasing, essentially, the variance of the Pacific climate system. Now, of course, if we look at marine heat waves in general, there was a nice important paper by Eric Oliver on the fact that mean warming, not variability, drives marine heat waves, which means that most of these kind of prolonged or intense heat waves are really connected with the fact that the mean climate is warming, and as such, like is shown here, you're more likely in the distribution of temperature to experience periods of time when temperature are higher than what we have experienced in the past. But the work that I presented today, especially for the Pacific, also suggests that there's an increase also in the climate variance, which means that even if you didn't shift the mean, the tails of the PDF are increasing, meaning that the variability of the climate system is also increasing. And this kind of mimics a little bit the literature on the hurricanes, for example, where it's not a change in the mean state, but it's really a change in statistics of hurricanes happening. So with that said, I'd like to summarize. I spoke about mechanisms of Pacific climate that drives these heat waves, in particular the intensity and the role of persistent weather, and the duration, the role of the coupling, these large-scale teleconnections between tropics and extratropics. I then presented some evidence about an intensification of the climate variance and also of the coupling of the climate modes that have an impact on the statistics of these marine heat waves. And then last, I discussed a few hypotheses of what is the mechanistic role of anthropogenic forcing in affecting these climate mechanisms. And in particular, the first hypothesis is this increased thermodynamic coupling associated with the meridional modes, more energetic meridional modes. that comes from this west feedback. And then the second one was really about this interaction between the Kuroshio and the Central Tropical Pacific associated with the shift in the storm track, which is more likely to really activate the coupling between these two and make it more energetic. Last, I'm not going to have time to talk about the marine ecosystem response to these more frequent ocean extremes. But if I had time, what I wanted to discuss is the fact that these extremes and this kind of increasing variance have a cumulative effect on the marine ecosystems, which have a long memory for all these kind of perturbation. And these cumulative effects essentially lead to an ecosystem amplification. And if some of you are interested in this kind of work, there's some papers that we have here. And so with this, I'm going to conclude and just leave you with a quick pointer to the fact that I'm currently, together with these incredible students and postdocs and other colleagues, we're writing a review paper for annual reviews in marine science that will come out in 2021, which really will describe these mechanisms of low frequency climate variability in the Pacific, really hopefully giving you a good idea of the mechanistic kind of view of climate in the Pacific. And thank you very much.